the stability of the phases is important not only with respect to the long term curing condition, but also when you start using these binder formulations, or when you want to have a research study where you want to address how the behavior of the concrete or the new binder which you are investigating tend to vary with respect to curing conditions. For instance, you do concreting on a hot summer in Chennai or a cold winter in Delhi, right. So, you tend to produce varying levels of these phases. So, X-ray diffraction can be a very useful tool in understanding the kind of hydrate phases that are formed with respect to curing temperature. So, here I have presented X-ray diffractograms of LC3 binder systems which are cured at different temperatures at 20 degrees Celsius, 40 degrees Celsius and 60 degrees Celsius. What you tend to see is the phases which are formed initially at when system is cured at 20 degrees Celsius, right, is reduced when you increase the curing temperature to nearly 40 degrees Celsius, and at 60 degrees Celsius the phases are not present. So, this leads to very interesting research questions to understand what is happening to this phase at higher temperatures, right. And also in the XRD lecture you would have been taught about quantification of the X-ray diffraction patterns. So, when you start quantifying the X-ray diffraction patterns, what you tend to see is the ettringite amount which is formed initially tend to reduce with curing temperature, right. The monocarboluminate increases from 20 to 40, but however decreases at this temperature. So, instead of carboaluminate, what you tend to start forming is the monosulfate, which is more typical of the system. So, when you start having higher curing temperatures, so sulfur aluminates become more stable than carboaluminates, right. So, in this way X-ray diffraction will be a very useful tool to understand the effect of curing temperature on the final phase assemblage, right. The variations in the formation of hydrate phases such as ettringite and carboaluminates, and also the influence of pozzolanic reaction can also be assessed. For instance, if you observe the calcium hydroxide peak here, right, at 20 degrees Celsius you still have a strong peak, at 40 degrees Celsius it is removed, and at 60 degrees Celsius you do not see much of the peak, because when you increase the temperature you accelerate the pozzolanic reaction. So, clay reactivity is increased with temperature, which tend to consume more of the portlandite which is present in the system, right. So, another aspect which we can understand with respect to curing temperature is what is happening in the binder as such. So, can we try to understand some mechanisms of how the different components present in the binder formulations is reacting, right. So, previously we discussed about formation of carboaluminates, looking at the clinker itself. So, you have clinker and you have clay. We saw pozzolanic reaction of the clay was accelerated, but when we start observing just the clinker phases, there is some interesting behavior which we can identify. For instance, here I have presented degree of hydration of the clinker phases, right. How this can be estimated? You can do an XRD, quantify the amount of clinker phases, which is the cumulative of your C3S plus C2S plus C3A plus C4 AF, right. So, when you take the summation of these phases at the initial time and at different intervals of time, right, and normalize it with respect to initial time. So, for instance, initially you have 100% clinker, right, in your system, so normalized value, and at particular instance of time at 3 days you have 60% which is remaining, right. So, your degree of hydration of your system would be at around 40% of your initial clinker phases has reacted. So, when you start observing with respect to temperature, you can see the reaction of the clinker phases is accelerated. So, this is for the OPC system, where you can see at 3 days, 7 days and 28 days there is steady rise in the degree of reaction of the clinker phases. So, when you cure at 60 degrees Celsius, around 85% of clinker has reacted. When you are curing at 20 degrees Celsius, about 75 to 80% of your clinker has reacted, right. Again, when you start moving towards your blended cements, you with fly ash, you again see a rise in the degree of reaction of your clinker, right. But interestingly, when you start using highly reactive pozzolans, for instance here calcined clay, what happens is your degree of reaction of your clinker increases initially, right, from 20 to 40 degrees Celsius, but there onwards it start decreasing, right. So, this can lead to variation in behavior, for instance stagnation of strength development in your concretes when you start using highly reactive pozzolan. So, when you use silica fume or calcined clay, strength tend to increase much faster at the early age, but you do not see much rise in the strength post some time. So, you need to understand what is happening when all these phases are present together, right. So, what happens is because the pozzolanic reaction is accelerated at high temperature, right, both the reaction of clinker as well as the reaction of pozzolan is competing for the space or formation of hydration products, right. So, once the reaction products are formed and filled up all the pore volumes, right, you have pore volume, it is all filled up with hydration products, you do not necessarily tend to react more of the initial anhydride phases, right. So, when system is cured at higher temperature, the porosity get filled up much faster. So, the clinker does not necessarily react when it is cured at very high temperature, right. So, interesting analysis like this on the different phases can be done to understand the use of the technique or the driving factor between the reaction happening in a composite binder system, right. Another interesting point of application is when you consider practical scenarios where different curing conditions are applied, for instance a steam curing condition in a precast yard, right. So, when you try to formulate concretes or binders which can be used in such condition and you want to use a new binder formulation such as LC3 formulation in such conditions, right. So, we already discussed it is having varying levels of chemical phases. So, how these phases can react. So, because of temperature the SC are the steam cured concrete at one day and NC are the normal cured, right. So, when you accelerate and cure it, what you can see is the ettringite phases which is present in the normal curing tend to get suppressed, right. So, the ettringite phases are suppressed and the carboaluminate phases are not seen very prominently in such conditions, right. So, this has to be dealt with and we can formulate our research studies based on the fundamental characteristics of the changes rather than direct application oriented scenario. So, for instance why the carboaluminate phases are lowered, right, what is the role of pozzolanic reaction in such conditions, right. So, coming into durability, here I have presented some quantitative X-ray diffraction results on samples which are exposed to sulphate conditions from one of my colleague Fatima. So, this is a microscopic image of the sample which is exposed to sulphate. So, you tend to see lot of damages on the at the surface and the core is intact, right. So, when you try to understand why the damage happens at the surface, so for instance if you look at the quantitative measurement at the core and surface, you can observe that there is formation of gypsum at the surface, right. So, gypsum for instance the blue here, you can see higher amount of gypsum which is formed in the surface. Presence of portlandite can be seen only at the core, right. So, portlandite which is here it is present at the core, it is present at the core in this system as well. Increase in calcite amount at the surface because it tends to get carbonated, right. So, the calcite amount are higher at the surface, right. And what you can also observe is in the case of fly ash and calcined clay binder, you do not have higher amount of this gypsum which is formed in the plain Portland cement. So, in plain Portland cement you have higher amount of gypsum, in these system you have lower amount of gypsum, right. So, this can be a very ideal way to explain the difference in the behavior of these binders when you expose to sulphate conditions. So, initially gypsum get formed and then lead to formation of ettringite, and when you have lower amount of sulphate moving in, you do not produce gypsum and ettringite. So, that can explain the expansion which is caused due to gypsum and ettringite formation in these binder systems, right. Similarly, when you start looking at other problems such as chloride for instance, so these are X-ray diffractograms of different systems exposed to chloride conditions, right. So, what happens in chloride is some chlorides are chemically bound within the hydrates, right. So, to assess the potential stability of these hydrate phases on exposure to chloride, we just immersed a thin section of sample in chloride condition for about 10% NaCl for 120 days and assess what is the progressive conversion of this phase. For instance, something called as Faridyl salt gets formed in the phase, right. So, when you start observing the X-ray diffraction pattern, you can see the one which is just cured and after exposure to chloride conditions, right. You can see the peak which is present for hemicarbo and monocarbo aluminate disappears and tend to produce a peak which is characteristic of AFM phase which has chloride, which is called calcium chloroaluminate or Faridyl salt, right. So, such phase transformation happens and you can see a stronger peak in the case of calcined clay binder because you have higher amount of the hemicarbo aluminate phases. So, you form Faridyl salt in fly ash concrete as well as in OPC concrete, but the amount of Faridyl salt formed in the composite binder with calcined clay and limestone is much higher because the initial phase composition with hemicarbo aluminate and monocarbo aluminate is also higher in the system. So, it helps conversion of these phases to Faridyl salt, which implies that there is higher amount of chemical binding of your chlorides on exposure to chloride environment in such systems, right. So, durability behavior in different exposure conditions can also be assessed by use of techniques. Next we will move into microscopy, where microscopy can be used to understand the material characteristics. For instance, here I have presented micrographs of clay, right. So, when you have micrographs, these are something called as EDX images, right, mapping images. You tend to map for different elements, right. You want to understand what is present in this raw clay, right. So, whether the clay is pure or there is some impurity, right. So, when you start looking at the ionic or elemental map of all these phases, you can observe the alumina and silica which are more generally expected to be present in clay, right. For instance, this large particle which is present here is purely silica, right, which implies it is a quartz particle, right. Also what you can see is large amount of these bright phases in iron, which indicates that there is a higher amount of iron in the clay. So, in this condition the clay which was used here have a color of reddish tint in it, right. So, pure metakaolin will be whitish in color, right. The clay which was studied here had a red color. So, when you want to understand why the changes in color of the clay, it is because of the presence of iron in the clay as impurities, right. So, if you want to understand different materials which are used and look at maybe impurities such as titanium and other materials present in it, microscopy can be a very useful technique to identify local distributions of these phases, right. And the next important characteristics where SEM is often used is to understand the morphology of the hydrates, right. We tend to see higher amount of yttringite formed, but where is the yttringite formed, right. So, here I have presented a micrograph of an yttringite precipitated in large voids of an LC3 systems, right. So, naturally we tend to believe that yttringites are long needle like structure, right, and because when you have a higher amount of alumina and limestone, you tend to have large amount of yttringites which is formed, right. And interestingly you can also tend to look at the changes between all these binders and try to come up with understanding why large chunk of these yttringites are formed in the large voids, right. So, when yttringite is formed at later ages, right, it tends to precipitate where there is free space, right. So, because you have a large void in these conditions, right, you tend to form a chunk of yttringite. Similarly, there are also theories which suggest that there will be deposits of Portlandite just along the interfacial transition zone of your aggregate and cement, right. So, to confirm yttringite, you can simply do an EDAX at one of these needles and it tend to confirm calcium, sulfur and alumina, right, which confirms that it is the yttringite phase which is present, right. The other feature apart from morphology is the micrographs itself, right. So, what all characteristics we can observe from micrographs. So, for instance, this is a micrograph of an OPC binder, plain Portland cement. So, you can see this large crystals here, right, and also large voids which are present, right. because you have this large crystals of hydrate phases which are formed and presence of Portlandite, you tend to see the structure is kind of loosely packed, right, and you can assess it to come up with the estimates of porosity, which I will discuss in a short time, right. So, when you start moving towards blended binders, for instance with fly ash, you do not tend to see greater amount of these large crystals which are Portlandite, right, and also we can observe a lot of this circular faces which are very typical of fly ashes. Interestingly, what you should also look at is the local densification which is there. For instance, lot of finer amount of this hydration products which are formed, right. So, which are typical of the pozzolanic CSH which is formed in the system. The bright phases are the unreacted phases, right, and the hydrate phases are the ones which are present in the in this zone, right, with grayscales. And when we start looking at micrographs with calcined clay binders, for instance this is an unreacted clinker, you have the zone around the clinker which is your inner CSH, right, and you can look at the capillary region which is the interparticle region, and the amount of hydrates which is formed and the packing of hydrates, right. So, compared to the plain Portland cement system where you tend to have a lot of these large crystals, you find much of the fine grained species in the or hydrates in the case of calcined clay binder, which tend to produce a very dense structure, right. So, physical comments like such about the packing of the structure, the amount of voids which is present can be made by using micrographs extracted from SEMs, right. But can we extract quantitative information? So, for instance this is a raw micrograph of an OPC binder, right. There is a process called segmentation which will be covered in the image analysis lecture, right. So, when you do segmentation you can split out phases which corresponds to different grayscale, right. So, you have a brighter scale and a darker scale, right, and a black spot which is porosity. You can segment all these phases. Once you segment it, you can separate out and extract only the porosities alone, right. So, you can get estimates of porosity by doing processing of these images, right. Naturally in such condition you are looking at very minor scale, right, the scale is about 50 micron. So, in order to get a representative analysis, it is necessary to do at least 30 to 100 images and then take the overall assessment of porosity in such cases, right. So, basically when you want to come up with porosity assessment with micrograph, making sure it is representative of the system is very critical. So, you need a sufficiently large number of images to process, right. So, here I am just giving a typical presentation of the kind of porosity which is present in different binders. So, you can see large amount of this white spaces, right, and here lot of fine grained porosity because of the packing, right. So, how is this processing done? Though this will be dealt separately because I have introduced it, I will just cover it up a bit quickly. So, you tend to produce a grayscale image from the microstructure, right, which is having varying levels of grayscale. So, grayscale for an 8-bit image will vary from 0 to 255, right, 255 is bright white and 0 is black, right. So, you tend to get an image like that, right, and then you can fit an arbitrary threshold for your porosity, right. So, in this case it is fixed at 0 to 61, right, and segregate all the phases corresponding to that region, and the remaining phase, for instance you can separate your phase from here to here which corresponds to your major dominant CSH, right, and then the second peak which is here which corresponds to your calcium hydroxide, and the last region which corresponds to your unreacted clinker phases. The brightest phases which are present in your micrographs are unreacted phases. So, in that case we can get estimates of your different volume fractions of the phases, 4% of porosity, CSH about 60% coverage, calcium hydroxide about 20% and 12% of unreacted clinker which is present, right. So, assessment like that can be made with help of micrograph and understood the local distribution of hydrate phases. So, for instance you can make a cumulative image of all those 4 phases together and produce a cumulative image which can be representative of the spatial distribution of different hydrates in your microstructure, right. So, one part of the imaging is microscopy is to do the imaging and understand the characteristics of the physical structure, right, and also there is a mode of operation in SEM called EDX, right. So, which was covered during the theory part of the lecture, right. EDX will give you local chemical composition of your hydrates. So, for instance, if you go back to your micrograph, you pick a point here and do an EDX assessment, you pick a point here, you do an EDS assessment, here you will get an EDAX assessment of the C3S clinker, right. Here you will get the chemical composition of your CSH, right. So, when you want to understand is there any variations in the CSH formed in the plain Portland clinker reaction and pozzolanic reaction, right. So, what I have done is I have presented your CSH composition in terms of calcium to silica ratio, right. So, when you look at only plain Portland cement, the mean value, so this was done over about 100 points nearly, right. You can see the number of samples to be representative, the value is about 1.8, right. When you start using fly ashes, the value comes down. So, with respect to curing ages, you do not see much difference with respect to standard deviation, the value comes down from nearly 1.8 to 1.4, right, which indicates that you have less calcium in your CSH or more silica from fly ash has gone into your CSH, right. When you start comparing your fly ash system with your calcined clay system, you can see that the value has come down even further to nearly 1.3, which indicates that your CSH has even lesser calcium in it, right, because of the reactivity of the clay, higher amount of your silica and alumina species have gone into your CSH, right. This can hold importance in explaining behavior in different exposure. For instance, when you have decalcification kind of mechanism, for instance removal of calcium on exposure to sulfates or on exposure to carbonates, right. In those conditions you tend to have the systems with lower calcium to silica ratio losing calcium much faster, because it has lesser amount of calcium buffering in the CSH itself, right. Such fundamental informations can be understood by doing the chemical composition analysis. Again, going back to the curing, we discussed that there is difference in the phases, but there is also difference in the microstructure which is formed. So, we saw previously by using XRD you can quantify the degree of reaction of your phases, right. So, when you look at the hydrate phases, this is OPC cured at 20 degrees Celsius, you see less amount of these voids. At 40 degrees Celsius there are more of these voids. When you start curing at even higher temperature, you start forming large number of these voids, right, because the CSH is forming much faster at a faster rate, right. The CSH composition tend to vary, right, it becomes more crystalline or it becomes tend to have higher amount of calcium in the CSH, right, because of which you lose the dispersion of your CSH in your system, which increases the overall porosity, right. So, when curing temperature is higher, the overall porosity of the system can be higher despite the increase in the degree of hydration, right. So, calcium silica ratio tend to increase, but if you look at an OPC system, you tend to see like this is alumina to calcium ratio, you see that the distribution is almost concentrated in this zone itself. There is no change in the CSH composition, especially with respect to alumina in it. When you start looking at calcined clay binders, right, because you have alumina, the clinker reaction is accelerated and the clay reaction is also accelerated, right. When both are accelerated, what happens is because of the clay reactions, you tend to increase the alumina content in your CSH, right. And I was also talking about reduced degree of hydration of your clinker phases in calcined clay system. So, if you look at the micrographs, this is at 20 degrees Celsius, at 40 degrees Celsius. When you start looking at 60 degrees Celsius at the same scale, you tend to see large amount of this unreacted clinker grains which are present in your system, right. So, more alumina goes into CSH because of higher reactivity with respect to temperature, right. Another case point of contention to explain is how is this CSH composition relevant. So, for instance, if you look at the ternary chart, you can make charts like this which can explain the variation in microstructure. For instance, it is related to your pure phase diagrams of different hydrated phases that can be present when you have calcium, silica and alumina, right. So, you have Portland cement which is present in this region, right. When you start forming CSH, typically this in a Portland cement the CSH will be in that in this region, right. When you start adding pozzolans which are rich with silica and aluminum, the CSH phase tend to get shifted towards this region, and in the case of LC3 we saw you can start forming phases which are almost at the mid of this region, which are Stratlingite phase, right. So, the one variation which this can cause is because you are producing a different characteristics of CSH, right, you tend to control the property development unanimously on all the concretes which are made with this such system. For instance, here I have presented one of the performance parameter called resistivity, which is a bulk response. So, the band indicates the response from 5 different sets of concrete, right. So, because the clay is reacting much faster, you can see the value has raised between 3 to 7 day itself, and it is much higher across the age. And when you start using fly ash binders or slag binders, right, the value tend to rise much lower, right. So, these are varying levels of concrete produced with the binder, which indicates the role of the material which is used to make concrete, right. So, when you understand what is leading to this major rise, right, anonymously on all the kind of concretes which are made, so it is related to basically your microstructure which is formed because of the binder ingredients in the binder, right. The last point of discussion is to understand durability behavior, right. So, in we saw XRD for chloride analysis, this is SEM for chloride analysis. So, what we have done is an EDAX scan, right, EDX scan from your cement grain till your outer CSH point, right. So, this indicates the distance from your cement grain to your outer CSH point. You can see near the cement grain there is not much chloride, the count indicates the chloride content, right, chloride content percentage. You can see near the cement grain there is not much chloride bound, but when you start coming far, right, in the outer CSH region you have high amount of chloride which is bound. In the case of calcined clay binder or fly ash binder, you can see local peaks like this in different zones, right. These indicates the reaction of chloride in the outer CSH region to form calcium chloroaluminate phases, right. So, when you have certain phases which chloride which is formed, you can have local increase in the chloride content which can be traced by using an EDAX technique, right. So, we have discussed about application of the characterization technique dealing with range of different problem with respect to one binder, right. What we have tried to do is what I have tried to do is explain to you the use of what, why and how. So, we have dealt in each slide, right, a different practical problem which is brought down in terms of scientific questions and explained by means of characterization tool by doing a proper analysis. So, when you are dealing with characterization, the major point is coming up with the right question, right. So, what is the change in the behavior which you want to explain by using the characterization tool, right. So, that will lead you to choice of proper characterization tool, right, and also bridge or use the characterization tool to bridge the critical knowledge gap in research, right. Merely a run of experiments alone cannot answer all the questions, right. Your questions should lead to your experiments which can answer the behaviors in some content.